Okay, let's start. So today I will talk about results of complete and precision loop, and we will talk about embeddings of Heisenberg. So I will start with some basic definition. Let G be a linear algebraic group. And then equivariant embedding of G is a regular open embedding of G into some algebraic variety X, such that the action of G on itself by left multiplication can be extended to an action of G on X. We discussed many times some equivariant embeddings, and we discussed a lot equivariant embeddings of the group GAN. So let me recall that by GA I mean the additive group of the field. Then GAN is a product of GAs. And I recall that this is a Hassett-Tschinkel correspondence. Which says that there is a one-to-one correspondence between the following objects: equivariant embeddings of GAN into projective space Pn. And local associative commutative algebras A with unit and dimension over C is n+1.
Just a small comment that this is an unusual definition of equivariant embedding. Usually by equivariant embedding we mean open embedding with two-side action.
Well, maybe, yes, maybe you're right.
For commutative group it doesn't matter, so in this GAN case, but these guys they started to consider non-commutative case. But they solve more general problem when you can extend only a left action. Okay, this is up to them.
So I will recall what is local algebra. Well, today we will talk not only about commutative algebras. So general definition of local algebra. So let A be associative algebra. Yes, with respect to multiplication.
Associative.
Associative, yes. A is an associative algebra with unit probably, yes. And unity, yes. Then we say the A is local. If there is one maximal left ideal. A unique but it's known that in this case this maximal left ideal is actually a maximal right ideal and it's a maximal just ideal. Let's call it M.
Right now the application map it to another idea.
Yes, I think the proof is a little bit more complicated. It's Jacobson radical, yes. In this case, it's a Jacobson radical, and it's known that Jacobson radical is two-sided. Well, that was an example of algebra which has the unique ideal, but which is not a local algebra. Is, for example, the set of square matrices. There is only one maximal idea. There are a lot of maximal left ideas. And I will talk how this correspondence looks like because I will need it. So we know that the group of automorphisms of a projective space is a for example, the set of triangular matrices of this type. And actually, today we will work with the set of nilpotent. All other matrices are convertible in this, so it's clear that. So the morphism of P is GLN plus 1, which is GLN plus 1 quotient by scalar matrices.
Scalar matrices and nilpotent matrices, and they commute, so this is a commutative algebra.
Wait, no.
Maybe the diagonal elements are equal or not? Maybe you have
Different, yes.
Three-dimensional algebra.
Yes. This is strange. I actually always thought this is not a commutative. But yes, this is a commute, yes.
I said the same arguments for this algebra. All elements are
No.
I'm sorry. It's not a Jacobson.
Okay. Well, we anyway will see a little bit more complicated example of non-commutative algebra. Let's see this. So, and if we have a GN action on Pn, then we have an embedding of GAM into the group PGL n plus 1, and we can consider the canonical homomorphism and then the preimage of GAM is a subgroup in GLN plus 1, which is isomorphic to one-dimensional torus, which consists of scalar matrices GAM. And let's call this subgroup H, and then we have Lie algebra of H, which is a subalgebra in the algebra of matrices, and we can generate by H an algebra. So today I often will write by these brackets algebra generated by this set. Yes, associated, yes. And it's clear that it's a local algebra because, well, we can think that H is contained in nil triangular matrices. So, and if we can intersect A with the set of nil triangle matrices, we obtain a maximal ideal in A. All other elements will be invertible this ideal, so it indeed will be a maximal ideal, and dimension of A is indeed n plus 1. Well, we add scalar matrices. Yes. Dimension of A is n plus 1. And because we can consider from A to Cn plus 1, yes, so we assume that our projective space is a projectivization of Cn plus 1, and we know that there is an open orbit which is isomorphic to GAN, and we can consider a point in this orbit. And this point is an image of some vector v from Cn plus 1.
A is commutative.
Yes, yes, in this case, A is commutative, yes.
H is the Wolf image or just this n-dimensional additive part?
H is n-dimensional additive part, yes. So we have a map which sends A to AV. And since this orbit is open, we have all scalar matrices So it's not difficult to see that the image of this map is n plus 1. And the kernel of this map is trivial. Because if some element product of BV is equal to 0, then for any A from ABV is equal to 0, but this is BAV, and so we obtain that BAV equal to 0, but this is Cn plus 1, but only 0 element, only 0 linear operator acts in this way on Cn plus 1. Yes, so in fact we see that dimension of M is n, must be n, since dimension of A n plus 1, and we know that local algebra is a direct sum of one-dimensional subspace generated by unity and maximal ideal. So dimension of M is actually n. And in that, to see this correspondence to other direction, which is take some local algebra A, local commutative algebra of dimension n plus 1. So again, we know that this is a direct sum, and we can take some element from the maximal ideal M and consider its exponent. We know that all elements in maximal ideal are nilpotent. So this is a well-defined element of A. In fact, it's an invertible element of A. And we can define an action of additive group of M on A when M acts on A by its exponent. And it's clear that this additive group is isomorphic to GAN. And there is an orbit of unity. And it's not difficult to check that it will be subset of this form 1 plus maximal ideal M. So, and when this action is linear, so when we will act on projectivization of A, we have an open orbit which is image of unity. So there is a picture. So this is Hassett-Tschinkel correspondence. This is how we can describe equivariant embedding of GAN into projective spaces by local algebras. And let's
comment concerning your example of non-commutative algebra. Take 3 by 3?
yes, you're right. And there is a corollary. We know classifications, the classification of local commutative algebra of dimension to 6. And we know then when n is greater than 6, then there are infinitely many. Strictly greater, yes. So, yes. Infinitely many commutative local algebras of dimension 7. Wait. No, 6, yes. Look, there are infinitely many local algebras of dimension 7. Yes, so dimension of algebra is greater by 1.
You want to write here n
Of dimension n plus 1. Yes. Oh, yes, thank you. Of dimension n plus 1. So there are infinitely many equivariant embeddings of GAN into n. And Ding and Zhizhen-Lua decided to consider a little bit more complicated case. So let's consider not a commutative unipotent group, but a little bit more complicated unipotent group. But before that, let's note one thing. If we have some U is a unipotent algebraic group, and we consider equivariant embeddings of U into a projective space. That in fact actually we can again construct a local algebra in the same way. So we can assume that U is actually a subgroup in GLN plus 1. Again, we can consider the algebra of U. And we can generate associative algebra by U. And the same reasons show that this will be a local algebra, not necessarily commutative in this case. Local associative algebra with unit.
You may write just one. And two are the shorter, and no question whether it's a bidimension or multiplication.
Yes.
Can the dimension of this algebra be greater?
Yes, but in fact, the dimension of this algebra is unpredictable. So it's hard to predict what is the dimension of algebra. And if we want to go to other side by take some algebra, local algebra, and construct some equivariant embedding, we have to choose some space which generates this algebra. So in this case, this correspondence doesn't work well. But still we have some algebra. So, and now we'll consider unimportant group of special form. Today we will consider unipotent group of special form and actually embeddings of special form. And in this case, we obtain yes, not generalization, alternative version of Tschinkel correspondence. So we will consider Heisenberg group let's consider some even dimensional vector space. And let's take omega, it's non-degenerate, skew-symmetric form on W. Well, if you will see, if you
initially this is a Lie subalgebra. Lie subalgebra with respect to the Lie brackets. But when you multiply matrices in the usual way, you can obtain more.
yes, actually, you can just take some one-dimensional group GA, and in this case, you can obtain a algebra of. Well, if it's not an additive action, I mean, if we have no open orbit, if we just take some GA subgroup and generate it by it some algebra, then it can be the dimension can be not 2.
So, and this omega is just a symplectic form?
Yes, it's a symplectic form, yes. And we know that there is a basis in which the matrix of this form has the following way. And we define. Yes, E is identity matrix. And we define the Heisenberg group. H2n+1 in the following way. We take the set WXC and define the group operation by the following formula. So it's not difficult to check that this is indeed a group. Well, it's maybe a little bit confusing because many people know three-dimensional Heisenberg group, which is the group of matrices 3 by 3, unipotent matrices 3 by 3. But actually, one can see that this group is isomorphic to this group. So H3 is isomorphic to the group of such matrices, and we need to send this matrix to a pair of the following form. And one can check that indeed it will be isomorphisms between this group and H3. And in general, actually, Heisenberg group is isomorphic to the group of matrices of such form. So, and we can consider a Lie algebra of H. And Lie brackets are defined in the following way. Well, it's easy to check. And we see actually that is maybe the most simple non-commutative unipotent group, because it's easy to see that the derived group is one-dimensional, and it's actually a center of this group. And the quotient by this derived group is GA to N. This element's non-zero and this element's non-zero. C. No, it's maybe zero also.
I mean, in the derived subgroup.
Yes, exactly. Yes, derived subgroup consists. Yes, exactly. Yes. Mm-hmm. So, and let's consider equivariant embeddings of H to n plus 1. Yes, again into projective spaces. Yes. And we will consider not all embeddings, but we'll consider only embeddings with some special properties. And first, we know this any unipotent group is isomorphic to affine space. As algebraic variety. And it's not difficult to prove that complement to affine space must be some hyperplane in projective space.
Why?
Well, because the class group of P is Z, and on this open subset, any divisor is equivalent to trivial divisor. Yes. So any divisor is equivalent to complementary divisors. But it's not difficult to see that in this case, this divisor freely generate the divisor class group. So in this case, this must be only one divisor, and we know it generates Z, so it must be a hyperplane.
This might be a hypersurface, but it should be of degree 1 since it generates, so it's hyperplane.
Yes. So we have here open orbit. Let's call it big O. It's open orbit, and the complement to the open orbit is some hyperplane. Well, I will write it H. I hope it will not be confusing with R group. So,
non-equivariantly, this is just a standard embedding affine space in the projective.
yes, yes. Yes, and say that this hyperplane is a projectivization of some hyperspace V prime in this 2n plus 2 dimensional vector space. And first assumption, first restriction that we will have is that this derived subgroup acts trivially on this V prime. So let's call it restriction A. This subgroup C, we will call it C, which is a derived subgroup of Heisenberg group. And again, it's the same as center of this group. It acts trivially on V prime. Let's consider some non-trivial element.
How does the Heisenberg group act on the vector space of which projectivization is this?
Yes, we can actually uniquely lift because if we can consider canonical map from GLN plus 1 to PGLN plus 1 and consider
So this is because the group is unipotent.
Yes. The preimage of Heisenberg group will be always a direct product of such form. And there is a unique subgroup which is isomorphic to Heisenberg.
So this is the unipotent radical of this.
Yes, exactly, yes. So let's take some element C. In our subgroup C big. And let's fix some basis in V. And let's assume that our subspace V prime is a linear span of these vectors. And then C is a matrix of this form. And it's clear that we actually can choose a basis such that C will be such matrix. And in this case, the whole group C big consists of matrices of this form. And let's assume that in this basis we have C has this matrix. And then if we will act by C on some vector, then we'll obtain, obviously, let's write here C small. This vector, and let's call it, okay, if we take a map of this vector in projective space, then if we will send a C to infinity, then we will obtain just a point, the image of the vector E0.
So excuse me, could you please repeat the action? So do we shift just the first coordinate?
Yes, C acts by this matrix. And then it acts on this vector in the following way.
Why is the index n?
Oh, yes, thank you. N plus 1, yes.
Okay.
Well, it's easy to see that indeed in this case when... yes, thank you. 1 plus 1. So these points, they go to this point, the image of A0. If this coefficient is not 0, it's the case when this coefficient is not 0. When this coefficient is 0, then this is a vector from this subspace. So we, in this case, our point belongs to a hyperplane, which is a complement to open orbit. And if this coefficient is non-zero, then this point belongs to our open orbit O. So for any point inside our open orbit, we can act on this point by our one-dimensional group C, and we always obtain as a limit the same point for all points. And it's clear that this point belongs to complement to the orbit of this point. Let's call it O small. Well, and it implies that this point actually is invariant with respect to our group. Whole group, yes. Because if we
so the whole group needs to change this whole orbits, right?
yes, it interchanges surface of C, yes, so it must preserve this point. Therefore, the corresponding one-dimensional subspace is also invariant And we can consider an action of our group on the quotient space. And in fact, subgroup C acts trivially on this quotient space. And I forgot why. Well, it's something simple.
I think this follows from the matrix relation.
Well, yes, actually, you're right. Yes, indeed. Yes, when we go to the quotient space, yes, we can assume that we take just this block, yes, or this block. I don't know. I think this block, yes. We take quotient by 0, yes. So basically, yes, when we consider this action, yes, if we had some matrix, then we just take this matrix B. And for matrices inside C, we have obtained just identity. So actually acts quotient group, which I recall is commutative idempotent group. And
The quotient of H.
yes. Mm-hmm. And it's not difficult to see that if we take projectivization of the space, then we obtain equivariant embedding of this group. Well, this will be an effective action with an open orbit.
Why do we have an open orbit?
Well, it will be just an image of this open orbit in this space. And we discussed, so this action corresponds to local algebra, commutative local algebras. And there is a very simple local algebra. So we have a local algebra, we will call it B, and commutative local algebra of dimension 2n plus 1. And the second assumption is that we'll assume that this action is simple. So we have a maximal ideal in B. And we assume that multiplication inside B is 0 multiplication. Let's say that MB square is a 0 space. What does it mean? It means that actually we can choose the coordinates in this space. So this vector space is of dimension 2n plus 1, yes. Such that the action of this group is given by the following formula. So this condition on algebra B is equivalent that this action in some coordinates has this simple form. Well, in this case, this local algebra, which we can construct by action of our Heisenberg group, has a simple form. So again, we can assume that our Heisenberg group is a subgroup in GL to n plus 2. We have a Lie algebra of Heisenberg group, and we yes, n plus 2, I think, yes, and we generate by this Lie algebra associative algebra with a unit. And in fact, with these assumptions A and B, this will be 2n plus 2 dimensional algebra. So basically, there will be nothing except
So again, we add only scalars.
Yes, again we add only scalars, exactly. Well, and it's actually purely algebraic fact. It can be proved purely algebraic. So we have a homomorphism from A to algebra B. So in our basis, which we fixed before, our algebra A consists of matrices of such form, not all matrices. And we have a surjective homomorphism to algebra B, which sends a matrix A to this part. And then, with some algebraic technique, one can show indeed that there will be nothing else except this. And let's call this map psi. And the kernel of psi is actually, well, again, we have a subgroup C. And we choose a basis in which C consists of matrices of this form. And in our algebra A, there will be a matrix T, small. And the kernel of psi is a subspace generated by T. So both these facts not difficult to prove, but the proof actually is not very sophisticated. So just some algebraic manipulations, and it can be proved. We can choose a basis in A. Yes, moreover, let's note that M square, and M is the algebra of Heisenberg, in this case is also be the subspace. So let's choose a basis in our Heisenberg group, Heisenberg Lie algebra. So let's choose some subspace which is complement to this subspace generated by this T. Well, obviously it's a center of this Lie algebra. And there is a basis such that Lie bracket xy xg is some element inside T. Yes, let's say it's the value of our symplectic form W. Well, by definition of Heisenberg group, we have this symplectic form, and we have this basis. Yes, and we can choose a basis such that our symplectic form has a standard matrix. So this will be just some number. No, it's not this number. So in the same time, this product, and since M square is a subspace generated by this T, we obtain this. This product is some Aij T.
No, this difference.
And we can consider the corresponding matrix. Let's call it MA. And to obtain this equation, this matrix must satisfy this following condition. The following condition. And actually, we can take any matrix such that this condition holds and construct a local algebra with this multiplication by this matrix. Well, and actually it can be written explicitly. So I will probably not write down explicitly, but let's just note that for any MA, for any M, let's say, for any matrix M, such that MA, M minus M transpose equals to omega, then there is local algebra of dimension 2n plus 2 such that M equals to MA. Well, not just some local algebra, but again, local algebra of this form.
Is it unique?
By matrix,
The local algebra.
yes, multiplication, in some basis, multiplication is given by this formula.
So you mean the matrix uniquely determines the algebra?
Yes, this matrix uniquely determines. Well, actually, it's obvious, probably, yes.
Yeah.
Yes. Well, not obvious that. No, actually, it's obvious, yes. So, the question is now how many matrices do we have? So, we obtained that any equivariant embedding of Heisenberg group satisfying these conditions A and B, any such embedding is defined by matrix with the following conditions. And how many matrices do we have? And it's not difficult to check that embeddings are equivalent.
How many matrices up to what?
Yes, let's say up to what, yes. So embeddings are equivalent if and only if corresponding algebras are isomorphic, but it's equivalent that there is non-degenerate matrix C such that matrix corresponding to first embedding is C MA2 C transpose. So it's just a direct check by definition to see that this algebra will be isomorphic if this condition holds. So now we are interested in the action of this group on the space of matrices satisfying this condition.
Acting this way.
Yes, acting by this way, yes. Any such matrix, let's call it this set X. I think something to do. Any matrix M from X is a sum of symmetric matrix and skew symmetric. And it's clear that this difference is equal to MC, yes? So it must be equal to omega. So actually, this MC is fixed for all these matrices. So actually, this space is isomorphic to space of symmetric matrices. Yes? Let's call it by different letter, N. But now we consider not any. Yes, actually, the group that X on X is not whole GL to N. Yes, because we have this condition. Yes, So we want to that when we act on matrix, that must be equal to omega. And it's clear that it's again it's equal to this matrix. So it must be omega. So actually, yes, this group is symplectic. Yes. So
All group shall acts on X.
yes, exactly. Yes. So actually, we consider an action of symplectic group. Yes.
The second term must be transposed, right?
Here, yes. Thank you. So we want to know how many orbits we have when symplectic group acts on the space of symmetric matrices. But the determinant is not is invariant, so there are infinitely many orbits with respect to this action. So there are infinitely many embeddings of Heisenberg group into a projective space. Well, actually, there are infinitely many embeddings with these two properties, but this implies that there are infinitely many embeddings.
No, but answer is wrong, because two embeddings are equivalent if and only if there is a non-degenerate matrix C such that blah blah blah.
Mm-hmm.
It looks natural, so up to linear change this C.
Mm-hmm.
But then it turns out that C is not arbitrary, C should be symplectic. Something is strange.
Well, because embeddings are equivalent if we have such condition, yes. But in the same time, our matrix is not arbitrary. It must satisfy this condition, yes, this condition on difference. So if we act by some arbitrary matrix, then we will obtain some strange basis in our algebra. Yes, we choose a specific basis, and to obtain again this specific basis, we must act by symplectic group. Okay, sorry for maybe not a best talk, but this is all.
Okay, can you summarize? So what is proved in this paper?
Yes, in this paper proved that they say that their main result is that there are infinitely many embeddings of Heisenberg group with these two properties. But actually, if you they do not write it explicitly, but actually, if you look on the proof, you see that actually embeddings with properties are in one-to-one correspondence with such matrices or such local algebras of such form.
They classify all embeddings with this problem?
Not sure, yes, but I think yes. Maybe, but I think it's true.
So in particular, you can forget about this property. They prove that for any odd-dimensional vector space, a projective space, there are infinitely many equivariant embeddings of the Heisenberg group inside this.
Yes.
Okay. Are there any questions, comments? For those participants who like additive actions on projective space, non-commutative generalization. So what should be a dream? Dream should be able to have Hassett-Tschinkel correspondence, to say that embeddings are in bijection with some algebras. And this is some attempt. So this is not all embedding, but very specific embedding. But this matrices, this is something like substitute of the algebra because they correspond to such algebra. Okay, if no question and comments.